Welcome to the coverage of Chapter 1, and this is going to be a discussion of solar energy, seasons, and the atmosphere. So these are the topics that I will be covering: our galaxy and solar system, energy from the sun, the electromagnetic spectrum, incoming energy and net radiation, the seasons, atmospheric composition and temperature, the atmosphere's functional layers, variable atmospheric components, and anthropogenic pollution. So these are questions and related to this chapter, and I include them in each lecture. And so these are possible short answer questions for your exams. And instead of just giving a vocabulary or listing facts about something, it is a good idea for you to be able to tie in several facts and concepts in order to answer the question. So for instance, when we talk about why do we have seasons, you would want to talk about the movement of the Earth around the sun, the tilt of the Earth or axial parallelism, and the geographic distance that each location has from the equator. Okay, so starting with our lecture, when we think about Earth's place in space, we are in the outer arm of the Milky Way galaxy, and the Milky Way is a disc-shaped spiral of stars. Our sun is just one in 300 billion stars in the Milky Way. Our solar system condensed from a huge, slowly rotating and collapsing cloud of dust and gas, which was a nebula. And you may have heard about the Big Bang Theory, and it is related to this concept. So here is an artist's rendition of what the solar system looks like, and you can see that the line is pointing to our solar system in the Orion spur of the Sagittarius arm. And you'll see the arrow at the bottom says 100,000 light years. That means that it takes light 100,000 years to travel from one end of the solar system to the other. When we think about dimensions, distances, and Earth's orbit, the speed of light is 300,000 kilometers per second. A light year is where light travels 9.5 trillion kilometers per year. So that's the distance that light would travel in 1 year. And so the Milky Way is actually 100,000 light years from side to side. Our known universe stretches 12 billion light years in all directions, and the moon is an average of 384,400 kilometers from Earth, and it takes 1.28 seconds for light to reach the surface of the moon to your eye. So if you see a partial moon or a full moon, that is light that is coming from the sun, and it takes a little more than 1 second to reach your eye. Our Earth's orbit is an ellipse. It's not a perfect circle, but it's longer than it is wide, and we are closer to the sun in January, and we're further away in July. So here you can see some various planets that are arranged around the sun, and our solar system is 11 light hours wide. And you can see that the Earth is the third planet from the sun. And the bottom image is showing you, again, that elliptical orbit where it's not perfectly circular, but it is longer than it's longer than it is wide. And so our Earth is closest to the sun during the northern hemisphere winter on January 3rd, and we're furthest from the sun on July 4th. When we think about solar activities and solar wind, we consider the mass of the sun under immense pressure and high temperatures. Hydrogen atoms are forced together and energy is released. This is a process called fusion. The sun also produces clouds of electrically charged particles, and that is a solar wind. Sunspots are magnetic storms on the sun, and the number indicates the intensity of the sun, and they average an 11-year cycle between minimum and maximum. So this is a rendition of a solar eruption on the sun, and you can see in the top there the relative size of the Earth. On the bottom are different locations of sunspots in 2000 and 2009. Auroras are when solar wind interacts with the magnetosphere, which is Earth's magnetic field, and it generated from motions of Earth's molten iron outer core. The interaction of solar wind and upper layers of the atmosphere lead to a phenomenon called aurora borealis in the northern hemisphere and aurora australis in the southern hemisphere. The molecules are excited, and oxygen produces green or red flashes, and nitrogen will produce blue or red. So this is what an aurora borealis would look like. Again, you can see that the nitrogen is flashing blue or red, that oxygen is producing green or brownish red light, and in the upper right-hand corner, you can see what an aurora borealis would look like from orbit, from space. And this is an example of one over Whitehorse, Yukon, Canada in August 2012. Solar radiation occupies a portion of the spectrum of all possible wavelengths of electromagnetic energy. So wavelength and frequency do have a relationship with each other. Wavelength is the distance between corresponding points on any two successive waves, and frequency is the number of waves passing a fixed point in 1 second. The shorter the wavelength, the higher the frequency. So the relationship is inverse. The higher the wavelength, the shorter the frequency. So here is a representation of the electromagnetic spectrum, and you can see that there are relative sizes of the waves underneath the first row, which shows the names of the different wavelengths, and then at the bottom are examples of applications and different properties. So we have gamma rays, X-rays, ultraviolet, visible, near-infrared, shortwave infrared, middle infrared, thermal infrared, microwave, and radio. So radio waves are the largest at about 1 meter, and we go all the way down to gamma rays, which are at 10 to the minus 8 micrometers. Energy discharges from atomic nuclei down in the gamma ray area. Medical X-rays are shown next, and then visible light there's a light bulb that is showing you visible light to our eyes is white or bright, and you can see that visible light is actually made of different colors, the violet, blue, green, yellow, orange, and red. Infrared is heat, and you can think of the human body at 37 degrees Celsius or 98.6 Fahrenheit, or a heat lamp, and then most of us are familiar with the microwave applications of radar and television, FM radio, and AM radio waves. So the hotter an object, the shorter the wavelength. Sun's emissions concentrate around 0.5 micrometers, and 8% is made up of UV, X-ray, and gamma ray, 47% is visible light, 45% is infrared. The surface of the temperature of the sun is 6,000 degrees Kelvin, and Earth's emissions are centered around 10 micrometers. So here is an example showing you wavelength graphed against radiated emissions, and the units of this are watts per meter squared per micrometer. And it's indicating how much energy in watts per meter squared is generated per micrometer of wavelength. So you can see here that we have, looking at the very top, we have 8% ultraviolet, 47% visible, and 45% infrared. You look and find the terms at the top of the atmosphere and at Earth's surface. And there is a difference in energy coming into Earth's atmosphere and then interacting with Earth's surface. There's an absorption by CO2 and water vapor, and those are the troughs or the low areas of that graph. On the left, there is also an area that is absorbed by ozone. Insolation and the solar constant. Insolation is solar radiation arriving at Earth's atmosphere and surface, so it's energy, not heat, but it's solar radiation. There is a difference between heat, which is measured as temperature, and the units of that are degrees Celsius or degrees Fahrenheit, and insolation is solar radiation. It's measured in watts per square meter. There's a solar constant, or an average amount received at the thermopause, which is 1,362 watts per square meter. Less than half passes through the top of the atmosphere and reaches Earth's surface. Here is an artist's rendition showing you input of shortwave radiation from the sun to the Earth as yellow lines, and this is comprised of ultraviolet, visible, and shortwave, infrared. The red arrows are showing you output, which is long wave radiation from Earth to space. So think of this as heat emitted from Earth's atmosphere, and it is in the thermal infrared portion of the electromagnetic spectrum. There's an uneven distribution of net radiation because the Earth is curved, which leads to different sun angles. And this, in turn, leads to uneven distribution. A subsolar point is defined as that location where the sun is directly overhead or forms a 90-degree or right angle. And the location of the subsolar point changes with seasons, and it moves between 23.5 degrees north to 23.5 degrees south. That means that if you are further than 23.5 degrees north, the sun is never exactly overhead. It's never exactly 90-degree angle of those sun's rays. So here is a diagram showing you different surface areas receiving different amounts of insolation. And look at the boxes on the left. There's a bright yellow square at the equator, and then those rectangles get lighter in color as you go towards the poles. And annually, there's 2.5 times more energy at the equator than the poles. It's more concentrated and a smaller area is covered, despite the fact, if you look on the right, all of those arrows are drawn the same size, and those amounts of energy are equal coming in to Earth's atmosphere. When they land on different portions of the Earth, again, depending upon the curvature of the Earth, they will either be more diffused with a larger area covered at the poles, or they'll be more concentrated with a smaller area covered at the equator. So sun's rays arrive parallel to each other at Earth's surface, and you can see here that this is showing where the Tropic of Cancer and the Tropic of Capricorn are located. And the location of the subsolar point moves between those two geographic features. When we talk about global net radiation, it's the difference between incoming shortwave and outgoing longwave, and it is termed net radiation. It varies with latitude. The tropics have a positive net radiation, and it's highest over the tropical oceans. The poles have a negative net radiation, which means it's lowest over Antarctica. Here is a map showing you isolines, and there are numbers drawn on those lines, and an isoline is a line that is drawn through areas of equal value. You can see that there are some areas where there's negative value, and that means that more energy is going out to space than is coming in from the sun. And then there's areas where there's positive values, and there's more energy coming in from the sun than going out to space. So the positive values are found at the equator and tropics, and the negative values are found closer to the poles. So in this map, I hope that you notice that there is a color bar at the bottom, and it corresponds to the colors that you see on the map. So your negative values, or your areas where you're losing energy, are in shades of purple, and your positive values, or your areas of energy gain, are in shades of pink. Seasonality is due to the sun's declination, and the declination is the latitude of the subsolar point. It's also because there are changes in the angle of the sun and changes in the hours of daylight that we have during each day of the year. So here is a diagram showing you some reasons that we have seasons. So the angle of the sun above the horizon is called sun's altitude. On the June solstice, the angle of the sun above the horizon is 23.5 degrees, and at 23.5 degrees is 90 degrees. So that means that the sun is directly overhead and the sun's rays make a right angle. On the solstices, the sun's angle above the horizon at 0 degrees, which is the equator, is 66.5 degrees. So that's the angle of sun's rays. And then on the June solstice, the angle of the sun above the horizon again at 23.5 degrees south is 43 degrees. So in the northern hemisphere, in June, it is considered to be summer, but in the southern hemisphere, that is considered to be winter. And in the northern hemisphere, our winter is considered to be their summer. In order to determine the declination of the sun, there is a graph that you can read and interpret called the analemma. And if you look at this graph and find 0 degrees, which is the equator, you can see that September 25th has 0 degree declination of the sun. If you follow on over to the right, so does March 20th. And noticing that the months are on the inside of this curved line and the days are on the outside. So if you were to look for June 10th, for example, it is approximately 23 degrees north. And December 5th at the bottom is 22 degrees south. Make sure that you know how to interpret an analemma. So here are the main reasons for the seasons. Revolution means the movement around the sun, and that is the Earth's path that it takes around the sun. Rotation is the movement of where the Earth turns on its own axis. Axial tilt refers to the plane of the ecliptic. Our Earth is tilted at 23.5 degrees. The northern end points to Polaris or the North Star. Axial parallelism means the axis always keeps the same tilt, and sphericity is the shape of the Earth, which is curved. So here is that plane of the ecliptic, and you can see that the red line here is showing you where the North Pole is tilted. The orange line would be where the North Pole would be located if the Earth were not tilted, and that's what we mean by perpendicular to the plane of the ecliptic. And that revolution, you can see that arrow representing the movement of the Earth around the sun. So when we talk about circle of illumination, it is a way for you to think about areas that are in light and areas that are in dark. And if you are taking physical geography lab, you will probably explore this concept in more detail. And you can see that there are different areas that would be in sunlight, and there are areas that would be in darkness. And again, you can see that the tropics, the subsolar point, Antarctic Circle, and North Pole are all important in these aspects. What I want you to notice is that the portions of the Earth that receive more sun in summer are primarily in the northern hemisphere. That's represented on the left. And then the portions of the Earth that receive more sun relative to that are in the southern hemisphere. I'm sorry, in the winter. So here is a complex diagram showing you different characteristics that happen with the seasons. So we have our equinoxes and we have our solstices, June and December solstice and March and September equinox. And this diagram is showing you the circle of illumination as it changes with that Earth's revolution around the sun. So please take some time to review this and carefully read all the information on here when you're doing your review of your slides. So here are the facts that go with that previous slide. Winter solstice is December 21st. Vernal equinox is March 21st. Summer solstice is June 21st, and autumnal equinox is September 22nd. Notice that at the equinoxes, all locations of Earth have 12 hours of daylight and 12 hours of night, and the subsolar point is at the equator at 0 degrees. During the solstice, we have a subsolar point in the winter at the Tropic of Capricorn, which is 23.5 degrees south, and in the summer at the Tropic of Cancer, which is 23.5 degrees north. That's the summer solstice. Okay, moving on to atmospheric composition. What we think of as air is simply a mixture of gas, and it's odorless, colorless, tasteless, and formless. It's all blended so thoroughly that it behaves as a single gas. For practicality, the top of our atmosphere is 480 kilometers or 300 miles above Earth's surface. Beyond that is what's known as the exosphere or the outer sphere, a less dense atmosphere that is nearly a vacuum bounded by gravity as far as 32,000 kilometers from Earth. So Earth's atmosphere does have its own weight, and it presses downward due to gravity. Air molecules create air pressure through motion, size, and number. So all air molecules are in motion, and depending upon the size of them and the number that are in a given portion or a given volume of air, they're going to have different air pressures. Pressure is exerted on all surfaces that come in contact with air, and air pressure is approximately 1 kilogram per square centimeter or 14.7 pounds per square inch at sea level. So here is a representation of atmospheric composition and pressure profiles. So if you look at the divisions on the very left, there are two, the heterosphere and the homosphere. Heterosphere has distinct layers of gases, and the homosphere has well-blended gases. The pressure profile, or thermopause, is divided up into thermosphere, mesosphere, stratosphere, and troposphere. And then finally, if you look at the circles in the light blue polygon or rectangle on the right, you can see that there is a higher density and higher pressure of air when you are closer to the surface, which is 0 kilometers in this graph. As you move up in the atmosphere, there is less density and less pressure, and you can see there are fewer blue circles per area. So atmosphere is divided into two broad regions when we talk about gas or composition. The homosphere goes from the surface to 80 kilometers. The gases are well mixed, and the only exception is ozone concentration. This ozone layer will vary in where it's located between 19 and 50 kilometers. It has a vast reservoir of nitrogen. The heterosphere is on top of the homosphere from 80 to 480 kilometer altitude, and they are lighter gases that are not evenly mixed. It makes up less than 0.001% of atmosphere's mass. The major gases in the atmosphere are nitrogen, oxygen, argon, and carbon dioxide. And our atmosphere is 78% nitrogen. A lot of this nitrogen comes from volcanic activity. The oxygen is 21%, and that is the molecule that is responsible for photosynthesis. It is a byproduct of photosynthesis, I should say. It is the molecule that is responsible for us breathing and converting food into energy. Argon is only 0.9%, and it's from the radioactive decay of potassium. And carbon dioxide is 0.0393%. It's a natural life byproduct. So here is a representation of those figures and those percentages in a pie graph. This is an example for you of carbon dioxide and climate change. And we can see that the year is on the x-axis and the parts per million is on the y-axis. And this is parts per million of atmospheric CO2. It's been steadily rising, and it is now even higher than was last measured in this graph. It is increasing every year. Okay, so the atmosphere is also divided as temperature. So it's the same atmosphere, but the last one we talked about was gases, and now with temperature, we have the thermosphere, and we have the mesopause, stratopause, and the troposphere, stratosphere, mesosphere, and thermosphere. I'm reading up on the left side. So these are all different areas of our atmosphere according to those temperature profiles that you see. So the thermosphere is from 80 to 480 kilometers, and it has a high temperature, low density, and low heat. The mesosphere is 50 to 80 kilometers. The temperature decreases with height. It is the coldest portion of the atmosphere, and that's where you'll find noctilucent clouds, bands of ice crystals so high in altitude they can still catch sunlight after the sun has set. And then the stratosphere is 18 to 50 kilometers from the surface of the Earth. The temperature increases with height due to ozone layer. The troposphere or tropopause is from the surface to 8 to 18 kilometers, and this varies with season, latitude, and surface temperatures and pressures. The heat source is the ground. The temperature decreases with height, and it's 90% of the atmospheric mass. Weather occurs here, and the normal lapse rate is 6.4 degrees Celsius per 1,000 meters. That means every 1,000 meters you go up in the troposphere, you decrease 6.4 degrees Celsius in 1,000 meters. And it can vary with the environment, and that will be the actual lapse rate is called environmental lapse rate, and that's the actual change at any given location. This is an example of the ionosphere and the ozonosphere. So this is where the atmosphere is divided up into functional layers. It extends through the thermosphere and mesosphere. It absorbs cosmic rays, gamma rays, X-rays, and shorter wavelengths of UV radiation. And this changes atoms to positively charged ions. I also want you to notice that the different functional layers of the atmosphere block different portions of the electromagnetic spectrum. So gamma rays and X-rays do not reach through down to the ozonosphere. Ultraviolet does reach down to the ozonosphere, and the visible portions of light go the furthest to the surface of the Earth, and shortwave infrared energy also reaches the surface of the Earth. Now, some UV light does get through that ozone layer, but most of the UV light that is emitted from the sun is blocked by the ozone. So the ozone layers in the stratosphere, it's highly reactive oxygen molecules that are made up of 3 oxygen atoms. They absorb UV radiation and radiate it as heat. So here is an example of how the ozone hole is theorized to have formed. It was damaged by chlorofluorocarbons, and ultraviolet light hits a CFC molecule. It breaks off a chlorine atom. That chlorine atom attacks an ozone molecule. It pulls an oxygen atom off of it, and then the chlorine atom and the oxygen atom join to form a chlorine monoxide molecule. A free oxygen atom pulls the oxygen atom off the chlorine molecule, and then once it's free, the chlorine atom is off to attack another ozone molecule. So in this way, it's breaking up that arrangement of 3 oxygens, and it is just this chlorine destroys the ozone layer. So there was a measure in the stratospheric ozone losses, and the chlorofluorocarbons break down ozone. The hole is the greatest over Antarctica, and after the Montreal Protocol that asked for the reduction of the manufacture of CFCs, the ozone hole is actually getting smaller. There are pollutants in our environment, and pollution doesn't necessarily mean that it comes from man. But pollutants are defined as gases, particles, and other chemicals in the atmosphere that are harmful to human health or cause environmental damage. There are natural pollutants such as wildfires and volcanoes, as well as the decaying of animals and the breakdown of plants and dying living things. So you can see here is an example of a volcanic eruption on the left from space and on the right from the ground. And this adds, as you can see, plenty of particles and soot and gas into the environment. Here is atmospheric contribution from a forest fire. So there are natural factors that affect air pollution: winds, landscapes, temperature inversions, temperature increases with altitude. So here is an example of dust from the Sahara that is being blown out over the Atlantic Ocean. So dust particles from land can go quite long distances over the ocean. So here's an example of an inversion layer, and you can see in the upper part of this diagram that the pollution is mixing in with the atmosphere, but in the bottom diagram there's an inversion layer which is trapping a lot of that pollution, and this is caused by warmer air, and it's known as a temperature inversion. And on the right you can see what it looks like over a landscape. So anthropogenic pollution is made by man. It includes photochemical smog, sunlight interacting with chemicals in automobile exhaust. There's also industrial smog and sulfur oxides. Coal-burning industries produce a lot of smog. Sulfur dioxide interacts with oxygen and water to make sulfate aerosols and sulfuric acids. This is acid deposition. You may have heard the term acid rain. And particulates are small particles in the air harmful to human health. So here is an example of anthropogenic pollution as seen from space in the top image. And in some areas of the world, it is very severe. And this is an image from China where people are wearing masks to protect their lungs from the particles in the air. So here are some diagrammatic representations of anthropogenic pollution. So we have nitrogen dioxide from cars. We also have carbon monoxide from cars. And then they can interact with water to form nitric acid, which is acid deposition and acid rain. We also have photochemical smog depicted here. Some more examples of anthropogenic or man-made pollutions. Industrial smog produces particulates, carbon dioxide, and sulfur dioxide. This results in acid distribution. You can see that these particulates are going up into the clouds and reacting with water and producing an acid. We also have nitrogen oxide or nitrogen dioxide from combustion, and that combines with water to produce an acid. And the nitrogen comes from fertilizers and particulate matter. In 1970, there was a Clean Air Act, and in the United States, it established standards for national air quality, auto emissions and fuel economy, power plant emissions, and ozone protection.